All right, welcome everyone. Today we're going to continue talking about improper integrals, and specifically we're going to look at a few other cases where we have an infinite interval that we're trying to integrate over. So what did we do last time? Well, we looked at these what we called right-hand improper integrals, and this is where we were dealing with an interval of the form a to infinity, and we were trying to integrate a function f of x, which we know is continuous, over that entire interval. So how did we deal with that infinity as our upper limit? Well, we rewrote it as an actual limit. So it's the limit as b goes to infinity of the definite integral from a to b of f of x dx. So essentially we've taken this improper integral notation and we've rewritten it as two things. It's a definite integral here that we're going to do, but then also as a limit as that b value gets larger and larger, as our upper limit gets larger and larger. And what we saw is that for a non-negative function, we can interpret these improper integrals as the area under the graph. So in the case of these right-hand improper integrals that we looked at last time, it was starting at, say, x equals a, and from then on we found the area for that shaded region that starts at x equals a, is under our curve, and extends infinitely far to the right. Now, we can kind of produce the analog of this where we move to the left. And that's what we're going to look at. We're going to look at these left-hand improper integrals. Again, it's the same setup. We're going to be talking about continuous functions, but we're going to be looking at intervals now of this form. So starting at x equals b and extending infinitely far to the left. So the interval from minus infinity to b. All right, so we can look at the integral over that we can look at the integral of f of x over that interval. A lot of similar sounding words here. So we have the integral from minus infinity to b of f of x. That's our improper integral. How do we define this? Well, again, we have to treat that infinity special. So we have to break this up into really two separate things. It's going to be the definite integral, so just a regular definite integral from a to b of f of x dx. But then we need to let that lower limit, a, we're going to let that lower limit get larger and larger negative. So a is going to approach minus infinity. So this is the definition. These are our limit definitions for improper integrals. And just like before, if we're talking about a non-negative function, well, the improper integral, we can really think of it as being the area under the curve. So it's the area for this region that starts at x equals b and extends infinitely far to the left. All right, so we can think of these in terms of area, and we also use that terminology convergent and divergent. So, we also said convergent if the limit exists, so we're going to see that there's integrals out there where that limit does exist. So it's always surprising to me that we have these regions that extend infinitely far in one or maybe both directions. So we have these unbounded regions that actually have a finite area. And that's what happens. If this limit exists, we actually, this kind of unbounded region, this extends infinitely far to one direction, still has a finite area. So we could technically kind of squish it all down and have a finite area. It's always surprising to me. What about divergent? Well, that's if the limit does not exist. So we say the improper integral is convergent if it does exist, divergent if the limit does not exist. All right, so we have this new left-hand improper integral, but we're really going to treat it, we're going to calculate things very similar to how we did with the right hand. Now we can kind of go in both directions. We can extend infinitely far to the left and infinitely far to the right, and we get this new improper integral, which we're going to define right here. It's the integral from minus infinity to positive infinity of f of x dx. Now this is an improper integral, and it's really over all real numbers. So for the interval from minus infinity to infinity. And how are we going to handle this? Well, we're going to split it up into a left hand and a right hand improper integral. So we're going to split it up, do the integral from minus infinity to 0 of f of x dx, and then do the integral from 0 to infinity of f of x dx. So we split this up into the left hand and the right hand improper integrals. And, you know, we split it at 0 here in this definition just because 0 is usually convenient, but we can really split it up at any x value that we want. So if you wanted to do it at 1 or 5, you could. -5, you know, you could split this up however you want. Normally 0 is a pretty good one to use. Now, there is some condition here. So this improper integral is convergent only if both of these left and right improper integrals are convergent. So that's what we're going to do. So we're going to be looking at both the left and the right improper integrals. And they both need to be convergent. So if one of them is divergent, then no matter what the other one does, this whole thing is going to be divergent. So we're looking at this improper integral where we extend all the way from the left all the way to the right, minus infinity to infinity. We're trying to integrate our function over all real numbers. And graphically, what this looks like for a non-negative function is it looks like we're calculating the area under the entire curve. So the area that extends infinitely far to the left and infinitely far to the right. We're calculating the area of that region between our function and the x-axis. And again, we're going to see cases where this is finite, and probably see cases where it's not finite, it's infinite. So again, we know integration always relates back to area under the curve. All right, so when we calculate these improper integrals, especially if we go back to our left and right, this is where we get our hands dirty, is we're calculating limits at infinity. So let's go through and remember some of those important limits at infinity. This is just going to help us with our calculations. So we have these 1 over infinity forms, and these all go to 0. So we have these, 2 here for power functions. So we have 1 over x to the n in each case here. And it doesn't matter whichever direction you approach, x approaching infinity or x approaching minus infinity, that fraction is always going to 0. And this works for really any positive exponent. So if you have a fraction and the power function is and the power is a positive exponent there, well, then that fraction is going to 0. Now, you have to be a little bit careful when x is approaching minus infinity. So I guess there is sort of an asterisk here. There are some exceptions for when x is approaching minus infinity. So when this makes sense. So, if we had, say, 1 over square root x, so an even root, it really wouldn't make any sense to talk about x approaching minus infinity because we can't plug in negatives into that square root function. So, for the most part, these power function properties are nice and accurate. 1 over x to the n approaches 0, whether you get really large positive or really large negative. Just, it has to make sense. So if we were talking about 1 over the square root of x, it doesn't make any sense to talk about the limit as x approaches minus infinity for our purposes because we have a negative under the square root. So there are some exceptions, but for the most part, we want to remember these. Similar for transcendental functions, especially when we're dealing with e to the x, that's our most common one that we're going to be working with. The limit of 1 over e to the x as x approaches infinity is 0. And a way to think of these 1 over infinity forms is, another way to think of that is really 1 over a large positive number, or just a large number for that matter. So when we talk about 1 over e to the x, what's happening in e to the x? Well, x is getting larger and larger, so that means e to the x is getting larger and larger. And so we have this fraction where the numerator is staying constant, staying 1, but our denominator is getting really, really big. And so when we have that kind of setup where our numerator is staying fixed, it's staying at a fixed constant 1 in this case, but the denominator is getting larger and larger, well, then the overall fraction goes to 0. Now, this second one here, the limit of e to the x as x approaches minus infinity, this one might look a little surprising because it's the only one that's not a fraction or written as a fraction. But for this one, what do we have? We have e raised to a large negative number. And so what happens when we have e raised to a large negative number? Well, that negative portion is really telling us we're actually dealing with, we can think of it as that we're dealing with a fraction. So we could really think of that as e over a large positive. So e raised to a large negative is really the same thing as 1 over e raised to a large negative, and we know what that does. It goes to 0. So these are just two common ones that we're going to see. So it's helpful to kind of remember those. All right, what are some other ones? Well, we have limits where x is approaching infinity or minus infinity, but the actual function itself just gets larger and larger. So we call these infinite limits, and they happen, regularly with power functions. So the limit of x to the n as x approaches infinity is infinity. The limit of x to the n as x approaches minus infinity could be positive or negative infinity, so it depends on what the exponent is. So if it's an even integer, it's positive infinity. If it's an odd integer, it's minus infinity. And these definitions or these properties here really work for any exponent, any positive exponent. again, with that same kind of disclaimer that it has to make sense. So if this was like square root x, we're not going to be talking about the limit of square root x as x goes to minus infinity. It's meaningless for our purposes. So, for the most part, for power functions, as you move, x to the n, as you move to the right or to the left, they either get really big positive or really large negative. So this is true for most exponents where it makes sense. And then specifically, if we're talking about even integers, for this last case, it goes to positive infinity, and for odd integers, it goes to minus infinity. Some other common ones we see, limit of e to the x as x approaches infinity, that gets really big. Same thing with natural log. So the limit of natural log x as x goes to infinity also gets really large positive, so it goes to infinity. And then a few special cases. So inverse tan, this is one that shows up a bit. So the limit of inverse tan as x approaches infinity is pi over 2. And then if we go in the other direction, x approaches minus infinity, we get negative pi over 2. Again, it's just, probably just remember those. And then finally, these show up a bit also, the limit of just a regular trig function. So we have 6 regular trig functions, and we know they all oscillate in some way back and forth. And because of that oscillation, that oscillating behavior, the limit does not exist for each of those. So, it oscillates and it never settles down. So these are true. Just put in your favorite trig function. So the limit of sine of x does not exist as x approaches infinity. Limit of cosine of x does not exist as x approaches infinity. So just put in your favorite trig name right there. All right, so these are just some helpful ones that we're going to refer back to. Let's actually get into an example. So let's determine if the improper integral is convergent or divergent, and if it's convergent, let's find its value. So here we see one of those improper integrals where we're looking at all real numbers. We're trying to integrate this function over all real numbers from minus infinity to infinity. And so the way we do this is we first split this up into our left and our right improper integrals. And we have some, flexibility over how we want to do that. 0 is usually a good place to split things up. So we're going to do the integral from minus infinity to 0 of 1 over 1 plus x squared. And then we'll also look at the integral from 0 to infinity of 1 over 1 plus x squared. And so we have our left improper integral and our right improper integral. And if both of these are convergent, well, then we could just add their values together and figure out what the value for the one we're actually interested in is. So let's start with one of these. Let's start with the right. All right. So we're going to start with our integral from 0 to infinity of our function, 1 over 1 plus x squared. First step, before we do anything, rewrite this as a limit. So we're going to write this as the limit as b goes to infinity of the integral from 0 to b of 1 over 1 plus x squared dx. That's the first step. Key first step. The only way we can deal with infinity, we have to sneak up on it. We have to approach it. So we're doing the limit as our upper bound. B gets larger and larger positive. All right. So now that's the first step. Second step is to just go through our integration here for this definite integral just like we normally would. So all of our integration techniques are going to work here. And this one, the antiderivative is not too bad. The antiderivative of this function is just arctan. It's the inverse tan function. And it's b approaching infinity. So we found our antiderivative. Now we evaluate our antiderivative. Notice here that as I'm doing this, I'm always writing the limit down. So I'm not leaving the limit off. I'm always writing it down, going from step to step here. We still need to write it. We still need to include it. We'll get there. We're going to do it, but we at least need to include it going from step to step. All right, so now let's evaluate our antiderivative. So we're going to plug the top number in. So we get inverse tan of b. Then we plug in our lower limit, which is 0. So we get inverse tan of 0. And we can simplify this. So inverse tan of 0 is just 0. So that's going to be gone. So we're really just looking at the limit of inverse tan of b as b goes to infinity. And this is one of those special cases that we just looked at. So this is pi over 2. Right here. So it's just one of these special cases. Probably have these, memorized. All right, so that's good. So we just showed that our right improper integral is convergent. So what that means is we can go on and work on our left improper integral. So if we did all this and got that the limit did not exist or was infinite, then that would mean divergent, and we could just stop. So no matter what would happen with our left improper integral, if our right improper integral is divergent, then the whole thing is going to be divergent. All right, so let's actually now work with our left improper integral, and this might be slightly new. So this is going to be our first time working with one of these improper integrals. So let's start it off. We're integrating from minus infinity to 0. Our function is 1 over 1 plus x squared. That's our improper integral. First step always is rewrite it as a limit. So it's going to be the limit as a approaches minus infinity, and we're going to integrate from a to 0. And if you wanted to use b here, you could do that as well. Just make sure you're consistent. Really, that's the key thing here, is whatever limit, whatever variable you're replacing here on the limit, that needs to be the bound, the upper or lower limit that you replace as well. So just be consistent. You can use whatever variable you want. Don't use x because we're already using x, but as long as you're consistent, if you wanted to use t, you could use t. If you wanted to use w, you could use w. So whatever variable you want, just be consistent and make sure you're not using it somewhere else in the problem. All right, so this is our first step. Rewrite it as a limit. Now, once we've done that, we have this nice definite integral that we can do. And we know the antiderivative of 1 over 1 plus x squared. That's one of our elementary forms. That's just inverse tan. And then we're going to evaluate this from x equals a to x equals 0. And again, it's the limit as a approaches minus infinity. We found our antiderivative. We plug in. So top number goes in first, so we're going to plug 0 in first. And don't forget the whole part of the limit there. We need to know what is approaching what. Top number goes in first, we get inverse tan of 0. Plug the lower limit in, we get inverse tan of a. We know inverse tan of 0 is 0, so that's going to simplify. So we really have just the limit as a approaches minus infinity of negative inverse tan of a. All right. So notice step 1 was to rewrite it as a limit, and then all the other steps here in the middle were really just going through and calculating the definite integral. We still wrote our limit notation going through each step like this. And now we're at a point where we can actually calculate the limit. So as soon as we calculate the limit notation is going to be gone. So what is the limit of inverse tan of a as a approaches minus infinity? Well, what is it? Let's look it up. Maybe we remember it, but in case we forgot, limit of inverse tan as you move to the left as x approaches minus infinity is negative pi over 2. So we're going to put that in. It's going to be negative pi over 2. And so this ends up just being pi over 2. All right, so what does this show? Well, it shows our left improper integral is convergent, and the value is pi over 2. And so to actually calculate the integral we're interested in, we add the results together. So let's just put it all together. This is the integral we're actually interested in, from minus infinity to positive infinity of our function. We split it up. So we split it up into the left improper integral and the right improper integral. And we happen to find that each of these on its own was convergent, so we can actually add up the numbers. So the left value was pi over 2, the right value was pi over 2, and then adding those up, we get pi. And, again, function 1 over 1 plus x squared is a non-negative function. It's always above the x-axis, so we could really interpret this as being the area under the curve. And actually, let's see if we can find it here. The graph of 1 over 1 plus x squared is going to look something like this. So we're finding the area of the region that extends infinitely far to the left, the area of the region that also extends infinitely far to the right, and is between that function and the x-axis. That whole entire region has an area of pi. So it's always surprising when we have these huge unbounded regions that have a finite area. All right. So that's really it for improper integrals where we're dealing with infinite intervals. Maybe let's try one more example just to dust off some other limit techniques that we've worked with in the past. So we really have to go back into the recesses here. And in this example, we're going to use L'Hopital's rule. So we're going to see an indeterminate form with L'Hopital's rule. So all of those, remember, all those Calc 1 limit techniques that we learned and indeterminate forms that we've seen, we can still use those where applicable. So let's start by, this is just one of our right improper integrals. So very first step, we're integrating over the interval from 1 to infinity. Our function is x e to the negative 3x. Very first step, we write this as a limit. So it's going to be the limit as b goes to infinity. The integral from 1 to b. So now this is just going to be a nice regular definite integral that we can calculate. And our function is x times e to the negative 3x. Now when we look at that function, not only are we going to see all of our old techniques come back for calculating limits, we can still use all of our old integration techniques and all the integration techniques that we've been looking at. So when we look at this, we actually see a product. So there's an x here, there's some x's here. It's a product of an algebraic function and an exponential function. We can actually use integration by parts to calculate this. So not only can we use all of our old limit techniques, but all of our integration techniques, we might need to break into those as well. So we're going to do integration by parts. So let's just work with this integral. We'll do it off to the side because this is going to take a little bit of work. This is just a nice definite integral, so let's work with it. And as we've seen, when we have, for integration by parts, we need to choose u, we need to choose dv. And normally when we have an algebraic part and an exponential part, the algebraic part gets put with u, and then the trig or the exponential part gets put with dv as our choice. Why does this work so nicely for u? Because when we differentiate and calculate du, the derivative of x is just 1. So we end up with dx here. And then we can actually integrate this exponential function. It's -1/3 e to the -3x, just one of our k-form integrals. So let's actually apply the formula. So what does integration by parts say? Well, the integral we're trying to do is u times dv, and what we are going to see is that it's equal to u times v. So -1/3 times x times e to the -3x. And then we subtract and integrate v times du. And so we're going to end up with a -1/3. That's going to make this a double negative. So let's simplify that right away. We'll make this plus 1/3, bring the 1/3 right out in front, and it'll be the integral of e to the -3x dx. And then once we have that antiderivative, we'll evaluate from x equals 1 to x equals b. So we keep going, get the antiderivative of this. And it's just going to be another -1/3 e to the -3x. Not too bad. And then we'll evaluate that whole thing from x equals 1 to x equals b. And maybe before we evaluate, simplify as much as you can. So the 1/3 times the -1/3, I'd probably write that as -1/9. And you know what, looking at this, it might even be better to factor this. So let's actually factor. So when we look at this, there's a -1/3 e to the -3x here. There's a -1/3 e to the -3x here. We can factor that off. Again, it's not necessary, as usually most with our, as we see with most of our simplifications, but it's just going to help do this evaluation. So let's factor off a -1/3 and an e to the -3x. And what do we have left over then? Well, we're going to have left over an x, and then we're going to have left over a 1/3 from this other one. So we'll have x plus 1/3 left over. Again, not absolutely necessary, but it's just going to make the evaluation just a little bit easier. All right, so let's actually evaluate this, and we're going to put it in up here. So we're going to do the limit as b goes to infinity. We still are going to be writing that, but now let's do the evaluation. So top number goes in first. So we get -1/3 e to the -3b times b plus 1/3. Take the bottom number, plug it in. So we get -1/3 e to the -3, And then we get 4/3 when we plug it in here. And let's simplify this down a little bit. And we can really, this is going to be a double negative, so it's going to become positive. And let's multiply the 1/3 with the 4/3. And we'll put it in front. So we're going to have a positive 4/9 e to the -3. So I always like putting the piece that becomes positive, put it first. And then I'm just going to have this all next to it, just so I don't lose track of that negative. All right, so we're going to actually see how to do this limit. So this is going to take a little bit of work here. All right, so let's just write where we are. We're doing the improper integral of our function. And we've seen that it's equal to the limit as b. There was a bunch of work there. So let's put some dots just to indicate that there was quite a bit of work there that we had to do. And we saw that it was equal to 4/9 e to the -3 minus 1/3 e to the -3x times b minus 1/3. And let me make sure I get that right. Plus 1/3. There we go. All right. So now it comes down to doing this limit. And when we look at this, even though it looks kind of complicated, this is just a number. So this is just a constant. So as b is increasing, b is getting larger and larger positive, this constant, even though it looks kind of complicated, is not going to do anything. It's just going to stay constant. So really where all of the action is going to happen is over here where we see these b terms. So let's think about what's going to happen. Let's look at this exponential, e to the -3b. What is that going to do? Well, as b gets larger and larger positive, this exponential e to the -3b is actually going to go to 0. We're going to end up with e raised to a large negative, and we know that goes to 0. Well, what about this b plus 1/3? What's going to happen with that? Well, b is getting really big, so b is getting really large positive, and if we add 1/3 to a really large positive number, we get something that's also really big. So this is going to infinity. So what we have here is something that's getting really small, getting really close to 0, times something that's getting really large positive. And so this is an indeterminate form. So 0 times infinity is one of our indeterminate forms. We actually don't know what it's going to do. Either this thing that's getting really small might win, or this other term that's getting really large might win. So this is what we normally call, it's an indeterminate form, but we normally call it an indeterminate product. And the way we work with those is we try to rewrite it as a fraction. So let's see what we can do. Well, how can we rewrite this as a fraction? Well, we have this exponential term with a negative exponent, and negative exponents always should be kind of telling you, rewrite as a fraction. So that's how we're going to do this. We're going to, instead of having e to the -3b, we're going to write that as 1 over e to the 3b. So you want to write it as a fraction. All right, so looking at this indeterminate product, and we're going to rewrite that exponential as a fraction. It's our kind of our usual strategy. So we're going to write this as 1 over e to the 3b. And then this b plus 1/3, for right now we can leave it right next door there, but we can actually take that and put it in the numerator here. So we can write this as the limit of b plus 1/3 over e to the 3b as b goes to infinity. And now if we think about this, let's think about what each of these pieces is doing. So the numerator here is still getting really large positive. So it's going to infinity. And what is just this denominator? What is just e to the 3b? What is that doing? Well, now we have an exponential where the exponent is getting large positive, and so this exponential is also getting large positive. So we end up with one of our indeterminate quotients, infinity over infinity, and this always tells us it's still indeterminate, but we can use L'Hopital's rule. So what is L'Hopital's rule? Well, we just differentiate the top, differentiate the bottom, and see what that limit is. So we'll put a little h there to indicate we're using the rule. We differentiate the numerator, and we're differentiating with respect to b here because b is really our variable. So derivative of the top is just going to be 1, and then the derivative of the denominator is going to be 3e to the 3b. And we have this fraction now where we have 1 over an exponential, and that exponential term is getting larger and larger. So this is equal to 0. And that's one of our 1 over infinity forms, which we know all go to 0. All right, so it took a little bit of work to get there. But we were able to show, using L'Hopital's rule and a kind of a clever rewrite here, that this indeterminate product, 0 times infinity, in this particular case, the 0 term, the term getting closer to 0, wins out. And so what happens then is we have the limit as b approaches infinity of 4 over 9 e to the negative 3. Let's break this limit up using our limit laws. Bring the constant multiple 1/3 out in front. And this is the limit that we just calculated and showed that it's equal to 0. So the limit of this constant is a constant, so this is just going to stay the same. The minus 1/3 is a constant multiple, so that's just going to stay the same. And we just showed that this entire thing, that this entire limit, took a little bit of work, but that's equal to 0. So what do we end up with? We end up with 4 over 9 e to the negative 3 minus 1/3 times 0, which is 4 over 9 e to the negative 3. Whew. So some of these are, it really takes, we had to bust out the integration by parts. We had to do an indeterminate product here, use L'Hopital's rule. So, we had to do some work here, but we were able to get it. And so we were able to show ultimately here, if we follow along, it took some work, but we were able to show that this improper integral, once we calculated out our limit, was actually equal to 4 over 9 times e to the negative 3. So, some of these can take a little bit, especially when you have to kind of use another integration technique, or you have to do a little bit of work calculating the limits there. So that's a good one to break on. So next time we're going to keep talking about improper integrals. So there's a few other forms that we're going to be looking at. But where our function has infinite discontinuity, an infinite jump. So we'll see that next time. All right, we'll see you then. Bye-bye.